So, hi everyone, my name is Jack Koenig. If you've spent any time, around Chisel GitHub or Gitter or Stack Overflow, you've probably seen my name. I've been a maintainer for 5 or 6 years now, and I'm going to give a talk that I've titled Chisel Breakdown 2. And so the purpose of this talk is to teach developers of the Chisel code base about the implementation of Chisel itself. So this isn't really a talk geared toward users, although hopefully users will find it interesting. But the main purpose of this is for developing Chisel itself. Oops, sorry, can't go backwards. And I'm really going to focus on the weird stuff, because a lot of times when you're new to a code base, there's a lot of assumptions or a lot of things that you may not understand right away. And so I'm trying to highlight some of those to help anyone who wants to contribute to fix bugs or add features to help them understand what's going on. I will say this is a somewhat more advanced talk in that I'm assuming moderate knowledge of using Chisel and Scala. That's kind of important for Chisel developers. So if you are a user who is maybe new or you're less familiar with these things, that's okay. This talk may not be the most interesting talk to you today, but this will be recorded, and hopefully someday you can watch it and we'll get a lot of value out of it. And I apologize if this talk seems kind of unorganized. There's a lot of material to cover, so I'm going to jump around a lot. And I don't have a lot of time, so I may be a little fast. And an important purpose of my giving this talk is that the last time I gave this talk was 2 years ago, and a lot has changed since then, so we needed to update everything. All right, so let's just get into it. So, first of all, what is Chisel? I think hopefully most everyone watching this talk or at the conference live knows, but this is a slide that I've been showing for probably 3 years now. I think I borrowed the original version of it from Adam with some modification. And so if you've ever seen one of my talks, you've seen this slide. I'm not really going to dive into this too much, because this is kind of what Chisel is from the perspective of a user, or if I'm trying to sell Chisel to convince people to use it, whether they're in like the more management side of things, or if I just want them to try it out. So what I'm going to get into is, what is Chisel really? And this is like the actual implementation, what's going on under the hood, what are all the weird things to look out for. So really what Chisel is it's a library of Scala objects and classes for representing hardware. So you can think about it just like you may have a JSON library in Python or Scala or something. This is just a library. You have uints, we have our types, right? We have uint, essent, vec, bundle, clock, things like that. We have hardware like registers, wires, ports, muxes. And then we have, structure like a module. Module doesn't correspond to real hardware, but it's a unit of organization. Chisel is a hardware graph. It has its own internal IR that I'm going to refer to as Chisel IR. Now, this is not to be confused with Churtle nor Fertle, which you heard a lot about from Skylar. This is kind of an internal data structure to Chisel that gets converted to the better defined IRs, IR being intermediate representation. Chisel functions, whenever you call a function in Chisel like plus or and or something, it's actually constructing IR nodes and mutating global data structures. That's what's happening under the hood. And then this IR is emitted or converted to Fertle, basically. Chisel is now, this is more recent in the last few months, it has a compiler plugin. So it is not just a Scala library. We actually have something that runs as part of the Scala compiler. And that we use for naming and for AutoClone Type 2, which is brand new, just in the most recent minor release 3.4.3. And I'll talk more about these later. And then Chisel is a lean front end for Fertle. The idea is that it provides some abstractions to describe your hardware, and then you go to Fertle, and then you can compile that down to Verilog. So here's a little diagram of what happens when you're generating Verilog with Chisel. So you have some Scala code, right? You write your Chisel. Your Chisel is really just Scala. You're just writing code. And that Scala is compiled by the Scala compiler, Scala C, or you may often be using a build tool like SBT or MIL. And so you run compilation, and that generates Java bytecode or classes. That's what Scala compiles to, just like Java. You may also see a jar instead. A jar is just a zip of class files. So that is the first compilation. That's what we call Scala compilation, but you don't get Verilog yet. What you then have to do is run what we call Elaboration, which is running that Java bytecode on the JVM, which will generate Fertle, which could be serialized as a .fir or .pb file. Those are just serialized forms of the circuit. Sometimes if you're using Chisel, You may not actually see the serialized form in between, but this is kind of a step along the way. And then we run Fertile on that serialized format, or we can run it in memory on the JVM at the same time, and that will emit Verilog. And so from Skylar's talk, you could swap out this step with the fir tool that he's been working on, but the general flow that most people have been using for a long time is this one right here with the Scala Fertile implementation. So one thing that comes up a lot is like, there's a lot of steps here. So where can errors be caught in your design, right? Because you're trying to design hardware. And so where are the places that you may realize something's wrong? Well, the first place, and I have green here for the places that we like errors to be caught, and red for bad places. And then black is, there are just errors that can be caught there as well. So Scala compilation is that first compilation, and that uses the Scala type system. And so that catches some bugs, like you can't call addition on a bundle. You can only call it on a uint or an sint. During Chisel elaboration, we kind of have our own runtime type system, if you will, where we can catch some errors like binding exceptions, if you see those, or bad connections are caught when you run elaboration. During Fertile compilation, a few more errors may be caught, like initialization, which is that you have to connect things under every circumstance. Invalid reset, like you're trying to reset an async reset flop to a non-literal value, combination loop detection. Sometimes bugs may be caught during Verilog compilation. This is like, Verilator, VCS, or your synthesis tool running compilation. This is bad. This should never happen. We try to emit correct Verilog. So these errors are rare. And if you do see an error in Verilog compilation, it's a bug and you should let us know. And then occasionally, of course, but you will catch bugs in simulation, right? Nothing about what we're doing can stop you from accidentally putting an and when you mean to put an or. So obviously, waveforms are useful for debugging hardware. So now I'm going to walk through a very simple example of what elaboration looks like in Chisel to kind of help build understanding of what's going on. So let's say we construct a wire and we do a bitwise AND of two things and connect it to that wire. So what really happens in Chisel is that this wire is basically a function call. Not basically, it is a function call. And it's a function call that creates this IR node, this def wire of the right type. Then the next function call is that AND. And when that AND calls, it pushes a we call a prim op, a primitive operation, a bitwise AND op, as you can see there, of the two inputs. And notice that it is creating a name here. It creates this underscore wire underscore T. Now, this fact that this has a name that's not just underscore T underscore 1 is new in Chisel 3.4. It used to be worse, but now it has a better name. It's deriving it from what's on the left-hand side here. And then that connection is the next function call. The connection is just another Chisel function call, and it creates this connect op. So these are Chisel IR nodes that internally are called commands. And these commands are pushed into a data structure inside the containing module, which is called a component. So if you look in Chisel IR, you may see commands and you may see component. And this is what's actually going on when you run Chisel. This is how it actually works. So I mentioned, a bit about binding. I mentioned that some errors can be caught by Scala compilation, but I kind of mentioned that Chisel has its own type system. And that's what we sometimes will refer to as the binding. So due to the architecture of Chisel, and this goes back to a long time ago, as far as Scala can tell, so Scala, the language and its compiler, whenever we have something that is a Chisel type or a Chisel hardware value, they have the same type from Scala's perspective. And so in Chisel, we differentiate them via the binding. So what do I mean by this? If I construct, an 8-bit uint, this is just a type. This isn't a wire. It's not a register. It's not a port. It's just a type. And Scala thinks of it as a uint. If you pass that type to the wire, op, this is constructing a wire, right? Scala still thinks that this is just a uint, but Chisel knows that this is actually a value, right? You've taken a type and you've constructed a wire of that type. So if you were to ask Scala, are they the same type? It would say yes. But if you actually, try and check if they're equal with the Chisel equality, triple equals, you'll get a binding exception that the template, this val here is not hardware. And this is how Chisel checks its own internal type system. It's called binding, and you'll see a lot of code around binding. So now I'm going to talk a bit about the Chisel project structure just to help anyone if they're coming to look at the code. If you're trying to contribute, it's important to know where everything is. So Chisel is divided into several sub-projects. Part of that is because in Scala, a macro cannot be used in the same compilation unit within which it's defined. Okay, so we have some macros that we use that are very useful, but they have to be in a separate project from core, which is where the bulk of Chisel's implementation is, because we use them in core and you have to define them in a separate project. Now, for reasons I'll describe in a minute, we define a couple more macros inside core. So the rest of Chisel is in this source main Scala project. And if you really, the way to think about this is what's in core is kind of the internals, and what's in Chisel 3 is kind of like stuff on top of that. Things that don't really need to touch internals, like utils. The queue is just a Chisel module, so it doesn't need to touch internals. Same with the main function, the stage and phase, and the way that you invoke Chisel. Our tests are in source test Scala. There's a lot of tests in there. And then documentation is in docs. So I'll talk more about each of these as I go on. So macros, like I said, they contain useful macros. We have this one called runtime deprecated to help us print warnings during elaboration time as opposed to just at Scala compilation time. We have this Chisel name, which is the way we used to do better naming, although we have a better way now that I'll talk about in a bit. And we have the source info transform, which despite the name does not provide source locators. And that I know can be a bit confusing. And I will touch on this later because I think it's important for any developer to understand this. Okay, so core, like I said, is like the bulk of Chisel. It's where all the internals are. And it's also where, so all this internal stuff, which I'll talk a bit about the builder later, it's where that Chisel IR is defined that I talked about. It's where, you know, things like module, data, uint, wire, when are defined. And then two important things I want to touch on are compile options. I'll mention more about those in a minute, but the macro and materializer for it are defined here. And also source info. So remember, source info transform was a different thing. This is source info, which is the macro that allows us to determine what line of code you like declared your register on. And so why are these two defined in core instead of in macros? Well, they're defined here because it's so important that we propagate these from the user code, right? And they can be materialized automatically. If we didn't define them here, then they could accidentally be materialized. So if we didn't propagate them correctly, it'd be really easy for us to accidentally, you know, destroy your source locator and give you something like, you know, bits.scala line 1205. And you're like, that's not my code. That's Chisel's internals. And so to prevent us from making that mistake, we're taking advantage of that limitation of Scala that you can't use a macro in the same you know, compilation unit within which it's defined. So it won't let us make that mistake, which is actually incredibly useful. So source main Scala, which is what we just call the Chisel 3 project, is where your Chisel stage is defined. This is how you invoke Chisel. This is where the compatibility module stuff is defined. If you ever see import capital C Chisel, all of that's defined in here. This is where your utilities are. It's where aspect-oriented programming stuff is defined. And it's where the old fertile emitter is. It used to be we could only emit fertile as a string, but now we can actually compile to fertile nodes in memory. This code is old and probably needs to go away, but that's where it exists if you have some reason to modify it. So now I mentioned the plugin. This is new in Chisel 3.4. So this would not have been in my version of this talk from 2 years ago. So this is a Scala C compiler plugin. It runs as part of Scala compilation. So not just Chisel Elaboration, right, where we're just running the Scala code that you wrote. When you're actually compiling your code, we're part of the Scala compiler now. And this is two things. It has something called the Chisel component, which does really good naming. And I'll provide some nice examples of that later, much better than the reflective naming we used to have, especially if you use Chisel 2 back in the day. And then we have the bundle component, which is what sometimes I will refer to as AutoClone Type 2. And I'll talk more about this and show how it works. Someday I hope to implement more of the bundle features for performance reasons, but currently it's just for AutoClone Type. And then, you know, the most important directory, and I think the one that hopefully, if you take home anything from this talk, I hope you take home that the documentation is in the docs directory. And so if you find something on the website lacking, this is a place where you can contribute to it to help improve it. And what's really cool about this documentation is actually checked. We compile it and we run it. So all the code examples in our markdown are compiled and run, which means we make sure that they stay up to date. Because in the past, we had a lot of problems with their documentation always being wrong. It was always too old. And nowadays, you know, in our continuous integration, every PR, we test that the documentation still works. And this is really cool because, you know, you can run spt docs mdoc and then you can see the markdown that gets generated. And that generated markdown is what's hosted on the Chisel website. And I'll just provide a little example here. On the left here is what you see on the website if you look at bundle literals, which is in the experimental features page. And here, there's a little snippet of Scala and corresponding Verilog that if you were to write this code, this is the Verilog you'll get out. And I think that's pretty cool. I think it's really neat to be able to show exactly what you put in and what you get out and make sure it always stays up to date, because it's really easy for this stuff to get out of date. And on the right here, this is what the markdown actually looks like. So you can see that this is just Scala code in triple backticks and a little extra thing where we're actually running Verilog emission. And with this special decorator that we wrote, this Verilog decorator for MDoc, which is the tool that's doing this, this Verilog decorator makes sure it's wrapped. The output of this is wrapped in Verilog so that the syntax highlighting works. So I think that's pretty neat. And so if you want to contribute to documentation, here it is, and we can make sure that it actually works, which is really cool. So, now just like a lot of different topics that are, I think, important for any developer if you're looking at Chisel, at contributing to it. Chisel stage replaces what we call the driver. And I think the driver might still be there, but it's all deprecated and hopefully gone in 3.5. I'm not sure. But it lives in, source main Scala, Chisel 3 stage. Chisel stage, it's the user API for invoking Chisel. It's if you happen to use the Chisel command line interface, it's what's used by Chisel main. And it's really where a lot of utility methods for generating, for running, elaboration and generating fertile, or running elaboration and fertile compilation to get Verilog. It's just all those utilities. And we do have this class Chisel stage versus object Chisel stage. This is like kind of a bad distinction that we are trying to do away with, but this is what it currently means. The class Chisel stage writes files and is used for custom flows. So if you write new Chisel stage.emit Verilog, it will write files automatically. The object does not write any files. So if you do just Chisel stage.emit Verilog, it's useful for like just running in memory and just, for little examples and tests. Now, this is very not clear. Everyone watching this talk probably just thought like new Chisel stage versus Chisel stage. That's like not a good distinction. And I agree. We are working on replacing object Chisel stage because this is not a clear distinction. And we're adding functions directly to object Chisel 3, just like .get Verilog, to try and make it simpler and more clear. Okay, the builder, this is a very important, so that was user facing. So users may see Chisel stage. Users should never see builder. Builder is the internal mechanism of Chisel elaboration. You can think about it kind of like the runtime. Like whenever you run Chisel, the builder is doing a lot of stuff. It's kind of this internal entry point for Chisel elaboration. It has these things called dynamic context and Chisel context, which are essentially buckets of global mutable state. And I mentioned earlier how we're like, you're looking up the current module and you're pushing, an add node and a wire node and a connect node. And that's how all this works. They look things up via the builder. They go into the dynamic context. These contexts use these things called dynamic variables. And a dynamic variable is a way of making this global state thread local. So, mutation is something that you have to be careful with threading. So Chisel really is single threaded, but because of this thread locality, you can run multiple invocations of Chisel, and you could actually elaborate with a little bit of work, we could elaborate multiple modules at the same time. But fundamentally, there's a lot of mutation going on, and that goes through the builder. Compile options, I mentioned before, are how we implement Chisel 2-like semantics in Chisel 3. And I hope nobody's using this, but this is what Rocketship uses with the import C Chisel. If you're doing that, please don't. All of the new checks, all of the new goodness we can do is in lowercase Chisel 3. And so a lot of this is kind of like a band-aid for, old legacy code. But if you're a developer, you need to know about compile options. And Chisel 3 uses, if you do import Chisel 3 _, you get this explicit compile options.strict. And this is like an implicit value that gets passed to every function you call. And if you are using import C Chisel, you're using the not strict versions. And that's how we change the semantics of like, an operation. Like things work differently in C Chisel. You can mix and match these. And there's a test to show how to do it, but I wouldn't recommend it. But there is a fine granularity of features you can do. So source locators, I think, are one of the most important features, and a lot of the code inside of Chisel is dedicated to this. So remember I said the source info transform doesn't do the source locator, source info does. So how does this work? If you look at like bits.scala in core, you may see, the definition of and for bool. And you'll see the definition is just macro source info transform dot that arg. And then you'll see this def do underscore and, which is the exact same thing, except it has these implicits, the source info and compile options. I just talked about compile options, and then source info is the source locator. And then I didn't include it here, but the actual implementation of the function is here. So all that source info transform does is anytime in user code you see, bool.and or bool space and, it will replace it with do underscore and. Now, why is that useful? So basically, it is to overcome the fact that if you were to try to do a bit extract immediately after an and, see, these implicits are a second argument list. And so the Scala compiler will think you're trying to pass those arguments. So if we didn't have this replacement, if we just put these implicits on the original ampersand version, it would work most of the time. But if you tried to do this, like and a wire with some mask and then do a bit extract immediately, you'd get an error. It would say, it looks like you're trying to pass a source info, but this is an int, and that's the wrong type. And that's clearly not what you want, right? Almost no one ever wants to do that. And so by doing this macro replacement, it makes sure that you can write this, and this is what, these are equivalent. It makes sure that you can write this and do the immediate bit extract, and it still works and does what you want. So that's all the source info transform is doing that, making sure that you can do a bit extraction immediately after an operation. Okay, so traditionally naming in Chisel used Java reflection. So the way it worked is that, a module is a Scala class. So any val is a public field of the class. And so using Java reflection, you can look up all the public fields and look up their names. And that's how we could name your IO and your wire. But it didn't work for things that are inside any type of closure, right? So inside of a function, we couldn't say, this is named reg. That didn't work. It's not possible with reflection because this val never exists in the field or in the class. So now we have this thing called the Chisel Naming Plugin. And we used to have @ChiselName. If you watch the previous version of this talk, I tell you about Chisel Name. So the compiler will inspect your Chisel source code, find all data objects that are assigned to vals, and insert names and prefixes. So let me give this other example where I have just some function. I have some results. These operations are garbage. This is just to make the point. Calls the function, does an OR, and connects the results to the output. Okay. So if you run this today in Chisel 3.4 and on, you'll get some pretty decent Verilog where not only do we figure out X and Y, but we actually can prefix them based on the fact that you return it to result, right? Because you could call function multiple times. You could do val foo equals func. And it's nice that the X and Y from those two different calls don't collide, right? So we do this prefixing. Notably, we also do prefixing for temporaries, which really helps with the stability. If we cannot come up with any name for you, we can at least use the prefixes to make your Verilog a bit more stable. And that's incredibly powerful. So this is what the Verilog looks like, but how does this actually work? So what the compiler plugin does is it finds your code, it sees this val x equals a plus b, and it inserts a function call. It inserts this thing called AutoName recursively. This is an internal API. Please don't call this yourself. It finds that the name is x. It passes that as a string argument. It also says, and also we need to prefix anything over here with this name. And so it also inserts a call to prefix. And so your actual expression, a plus b, is being passed as an argument to the prefix, which is passed as an argument to the naming. So AutoName recursively will name the final value that's returned by this expression. Prefix makes sure that any names that come up in here get the prefix x. So in this case, there's no temporaries or anything. There's only a plus b. A plus b gets returned. It gets named x. Except that's not what's happening, right? You got result underscore x. So this is where the prefixing comes into play. So down here, when we call val result and it does the exact same transformation as above, right? It's going to name the returned value result, but this whole expression gets prefixed with result. So when we call func, we have a prefix called result. So when we do AutoName recursively x, it says, but we have a prefix result. So we're going to name this result underscore x. And that's how the naming works. So this is what the plugin does automatically. The last thing I'm going to talk about, and I know I'm running a bit short on time, is clone type. So first of all, what is this and why does it matter? So because of the way Chisel works, and because we have these types like this bundle, these are immutable objects, and we need the ability to create a fresh instance of the type in order to create hardware, right? Because this bundle is some type, and I pass it to IO, and I need this IO object needs to be a different object than gen, because this is a port and this is just a type. Same thing with wire. I can pass gen to wire as well. And IO and W are different objects. I can connect them. So we need the ability to create copies of any object. So clone type fundamentally is an implementation detail. It's not useful to the user. It is something that we really don't like the fact that you even ever see issues with. Now for all the internal types like uint, clock, whatever, all the types that we've defined, we've implemented it ourselves. But the problem is that user-defined types like bundles and records need to have clone type too. We need to know how to clone your type. It's very formulaic, right? Many of you have probably written this where you had some bundle, you have some argument to it, and you have to override clone type, and just all you're doing is constructing a new instance using the most obvious thing. It's very obvious what you need to do, but it's annoying, right? And it's bad because you can forget. If you add a new field here with the default value, you may forget to propagate it here. It's very error prone. So the plugin now does AutoClone Type, which we'll call AutoClone Type 2. There was a reflective version of AutoClone Type that I talk about in the previous version of this talk, which you can find on the internet, a recording. It was a masterpiece is what I like to call it, because it was doing so much amazing stuff while also being extremely sketchy that this new version of AutoClone Type is a lot more principled and a lot better. It works for non-val parameters, which the previous one did not. It works for inner classes, which the previous one did not. And it's much faster because reflection is slow and this doesn't use reflection. So now it's extremely fast. I'll note that this was just introduced in the most recent minor release. It will be the default in 3.5. The only reason it's not on by default is that it's technically a backwards incompatible change. I don't have time to get into why that is, but it's talked about on the pull request. So we had to make it opt-in because we don't want to break people's code in a minor release. That would be crazy. But if you want to turn it on, if you look at the Chisel template, that's always the most up-to-date repo to look at to see the recommended build stuff. But you just need to add a Scala C option while you're using the Chisel plugin, and it will make sure that you turn this on. And this is great. We've been using it at Sci-Fi since it came out, and it's wonderful. And so just to show how this works, if you have your My Bundle from earlier, the compiler plugin generates two methods. It generates clone type impl and using plugin. The using plugin is for various reasons, just to it's basically that we have to keep the reflective stuff around while to make sure we don't break people's code. And so this just tells Chisel that we are using the plugin here. And it just generates that formulaic code. You may notice I didn't have the cast here. We actually, in bundle itself, we use the clone type impl and then we do the cast there. And that's just for implementation reasons. We could not figure out how to get it working. If this returned this.type, we just could not get the Scala compiler to do the right thing. Writing a compiler plugin is pretty difficult. And so this was the best solution we could come up with that worked. But this is basically all that it does. Also note that if you try to override these yourself, the compiler plugin will error and tell you not to do it, because it's really just for the compiler plugin to do. And then this is my last slide actually, is aspects. So I don't have time to dive into their details, but this is something that's new. I think we added these last year. And basically you can think, I showed how Chisel works where you have Chisel elaboration and then fertile compilation. Well, there's a phase in between them called the aspect phase. And this lets you write these things called selectors, where you can take the fully elaborated Chisel circuit and select certain pieces of it. You can say, I want all Q modules, or I want all whatever modules. Then inside your aspect, you can construct annotations for fertile. Now, you heard Skylar talk a bit about annotations, and your custom transforms can use them to do anything. And of course, built-in transforms may also exist to use them. But the idea here is that you have this way of post-processing or taking the fully constructed Chisel, Scala objects. And in a type-safe way, you can construct annotations to specify what work you want to do, right? And that work you may want to do is you may want to insert additional hardware. So without modifying your original source code, you may be able to insert profiling stuff or insert assertions, right? And keep that code separate. So you can use it to generate verification collateral like assertions. You can use it to generate physical design collateral like UPF or layout stuff. And so that's what these are for. It's just a way of separating the concerns of writing your Chisel source and keeping separate maybe your layout code that you've written against that Chisel. And so that's what aspects are, and those are another part of the Chisel code base. And so that's all I have. And I think I used up all the time. Sorry about that. But I think we're having technical difficulties with questions anyway. So hopefully, any questions can get forwarded to me, and you can feel free to find me on Gitter or send them to the Chisel users mailing list, and I'll do my best to answer them. Thanks a lot.